Thank you so very much. It's a great pleasure to speak here. And yeah, as pointed out, I'm at Uni Melb, and I work kind of across mathematical physics and physics in the area of quantum information connecting to other areas, such as quantum matter physics and here to quantum dynamics in the context of both integrable and quantum chaotic systems. So let me get started. I think I just need to select it. The key player of this talk will be the so-called bipartite entanglement entropy. And if you want to get an intuition what this is, let's just start from the thermal entropy that you know from statistical mechanics. So we remember from our statistical mechanics course that if you have quantum systems coupled to a big thermal bath at a fixed temperature, then in equilibrium, the state of the quantum systems is described by a statistical ensemble of energy eigenstates of the Hamiltonian in the system, weighted with some probabilities that depend on the energy and the temperature. And then we can compute the entropy associated to this probability distribution, and that's the thermal entropy that we know in statistical mechanics. Now let's look at a slightly different setup, namely a big quantum system, or maybe not huge, just a large quantum system, and now we focus on a subsystem. So it's not a system coupled to a thermal bath in equilibrium, but really just a quantum system with a pure quantum state, so it's isolated from the rest, and we just make our own choice to zoom into a subsystem and now only study the observables that we can measure inside the subsystem. And as it turns out, we can still describe the quantum state from the perspective of the subsystem as a statistical ensemble, but now not of energy eigenstates, but rather of certain states that depend on the state in the full system related to something called Schmidt decomposition. And again, we can compute the entropy associated to the probability distribution in front of these different states. And this is the entanglement entropy. We can compute it with a trace formula. And what this quantity, this non-negative real number tells us is how much quantum correlations there are between the subsystem and the complement. So really statistical correlations that you cannot explain by just classical statistics. And this quantity we will be studying in various, from various perspectives in this talk. Yeah? So this is the bipartite entanglement entropy. And let's look at an example of what we are doing. Let's look at 6 qubits illustrated here. And we split our systems in 2 equal halves, 3 qubits there, 3 qubits in the subsystem B. The Hilbert space is just C2. For each qubit, we have a 2-dimensional Hilbert space, and in total, we have 6 of them. So we get overall 64-dimensional complex vector space, this Hilbert space. Or if we describe it in real dimensions, we could draw this Hilbert space just for graphical purpose as a huge 128-dimensional real vector space, and the normalized states would form a sphere, a high-dimensional hypersphere in this space. And for each point on that sphere, we have a pure quantum state in the full system. And so we can compute this quantity that I just introduced, this entanglement entropy that describes for this state, this point on the sphere, how much quantum correlations are there between the first 3 qubits and the other 3 qubits. That's something one can compute, and we would find a number. And now let's repeat that for another state. And again, we find a number. And let's do it for 100 more, distributed over that sphere. We will get more. And now let's take the limit where we really sample over all states on the sphere, yeah, that with respect to the natural measure, the so-called H measure, and we will get a statistical ensemble, a statistical distribution of the entanglement entropy with respect to this system decomposition averaged over, studied for all states. And in general, we can compute the mean and the variance of this distribution, and already here for just 6 qubits, it looks pretty well approximated by a Gaussian distribution, but we expect that, of course, to get better and better for larger systems, but that's not even relevant for the discussion. The main point is we can compute the average and the variance, and we can now ask what happens if we increase the system, if we take the thermodynamic limit, not just 6 qubits. So we can ask, does the standard deviation divided by the average go to 0 in the sense that this Gaussian becomes narrow and narrow? And if that happens, we can really say that this average describes the typical property of all pure states in this ensemble, which of course means there will be states whose entanglement entropy is not here in the average, but those will be of a set of measure 0 in the limit of a large quantum system. Now, we can also now plot this average as a function of the subsystem size. Right now, we computed it for 3 versus 3. So this average is here in the center, and this black line is the theoretical maximum that the entanglement entropy can take due to the finiteness of the Hilbert space. So essentially, I'm just saying this number cannot grow arbitrarily large if the Hilbert space is finite dimensional. Now, we can do the same setup, same average, and so on, for a splitting of 2 versus 4 qubits, and we would find again an average, and we would find such a point, and we can do that also for 1, 4 qubits, and so on, and we would get a curve. And this is the page curve that describes the average entanglement entropy averaged over all states, over this sphere, as a function of the subsystem size. And one can show that it's always symmetric because the entanglement entropy is symmetric under exchanging subsystem and its complement. It really describes the mutual correlations between the two systems, and so it doesn't matter which one is A and which one is B. And now we can take the thermodynamic limit. We can increase the size. We take 12 qubits, 24 qubits, and so on, and we see that this average becomes closer and closer to this theoretical maximum. And this is an observation that Don Page showed 93, that the average entanglement entropy of a random pure state is close to maximum. And we will look at such curves for the rest of the talk several times and try to understand what this curve averaged over ensembles of states can teach us. But of course, we will not just look at the sphere of all pure states in Hilbert space, but we will look at subsurfaces of that sphere. For example, states that satisfy certain conditions, fixed particle number, states that are eigenstates of physical Hamiltonians, things like that. So we will evolve beyond just the average of a random pure state. And the claim is that that will teach us something about physics and dynamics of a quantum system. Okay? Any questions at that stage? Clear? Yes?
Is it obvious that the dependence is linear? Is that the dependence on the right corner plot is linear with respect to the V?
That this becomes a linear function? Yes, this is something that we will observe generically as leading order in the thermodynamic limit. Yes.
Is it numerically proven, or it can be also analytically demonstrated?
The leading, we will do an asymptotic analysis in large V, and then you can do everything analytically. I will explain exactly what we can do analytically and where we do comparisons to numerics. Yeah. Thank you. So this is this picture plotting entanglement entropy versus subsystem volume, and let's just go a little bit through the catalog of states that you can look at. So what I just showed was typical pure states, so really in the thermodynamic limit, all states in Hilbert space. Then something that people study a lot in quantum matter physics is not a random state in Hilbert space, but a ground state of a physical Hamiltonian. And they are shown to not satisfy a volume law, where the entanglement entropy increases with the size of the volume of the subsystem, but rather with the area of that region, which in such a plot for large V means area law is really here at the bottom, because it doesn't increase with the volume. So the coefficient in front of the volume is essentially 0. And that has been discussed at length already since the 80s, but there's a very nice review on the area law from 2010. Something that we started to study, and that is kind of the starting point of what I'm presenting here, is to look at translationally invariant quadratic fermionic Hamiltonians and compute this average not for all states in Hilbert space, but just for eigenstates of this Hamiltonian. And what we found was this curve, which for large V. For small subsystems, it looks very much like maximal, but for large subsystems, there's a big deviation between the behavior of a random pure state that's close to maximally entangled, okay? And the question of this talk is, what is this typical entanglement entropy for other ensembles, particularly focusing on fermions, and what can we learn from this? So the philosophy is, can we use these curves and the both analytical and potential numerical understanding of the entanglement entropy as a probe so that it teaches us about physics? And one prime motivation of this is the understanding of how isolated quantum systems thermalize. And of course, technically they don't. They are not coupled to a thermal bath, and they don't become exactly mixed density operator at a fixed temperature. However, if we consider a Hamiltonian H and some pure initial quantum state psi naught, and we take a physical observable, an expectation value, particle numbers in some region, magnetic field, some other properties that we can measure in our quantum system, and we study the time evolution of this expectation value, one finds that for many physical Hamiltonians H, this observable shows a behavior where over time it approaches a constant value. And this constant value you could have predicted without knowing exactly psi naught, but rather just knowing the energy expectation value of psi naught and then constructing the thermal state at a temperature that matches the energy of this initial state, which predicts the so-called thermal expectation value. And that's what people refer to as thermalization of isolated quantum systems. Not that the state becomes mixed, of course it's unitary evolution of a pure state, but that from a perspective of an observer who only has access to specific expectation values, you cannot distinguish the time evolution of the quantum system from a thermal state after a long time. And there is a reason why this happens, and there is some criterion when this happens, and that is when this Hamiltonian satisfies the so-called eigenstate thermalization hypothesis, or often simply put, is a quantum chaotic, meaning that the energy eigenstates of this Hamiltonian are in a certain sense sufficiently random distributed with respect to the eigenbasis of the physical observables one is typically interested in, such that under large long time evolutions, you essentially have constructive interferences of the many different energy eigenvalues that oscillate around e to the I omega t, and overall you then just approach the thermal expectation value. And of course, in principle, you can construct for every quantum chaotic Hamiltonian an observable that will not satisfy that, but they may not be physical in most situations. So for a physical observable, that's not so interesting. Now, in this talk, we want to look at this from the perspective of entanglement and entanglement of energy eigenstates. So what can we say? Well, in order to do that, we want to define physically relevant ensembles of quantum states that also respect the physical symmetries of the systems. For example, particle number conservation will be one focus point. Then understand the average entanglement entropy for these ensembles of states. So this would be, in the picture from before, submanifolds of your sphere. So just those states that also have fixed particle number, for example. Then use these families of states as a benchmark and compare if their entanglement properties matches the ones of eigenstates of physical Hamiltonians. And see if that allows us that, to make a statement about typical entanglement of energy eigenstates and how that relates to the question of if a Hamiltonian satisfies ETH or not. Yes?
Is it possible to put some sort of quantitative measure on how quickly this thermalization happens?
That certainly is possible. I mean, which also depends on the initial state. In fact, there are works that essentially take certain expectation values of polynomials of the Hamiltonian and its inverse with respect to the initial state and relate that to, for example, the initial slope, which gives a first approximation. It's not something I've worked on significantly, but I know that there definitely exist these studies. Yeah. Yes?
Are there any constraints on this initial state for this to occur?
A priori, not super strong. I mean,
because, I mean, if the initial state was an eigenstate of this Hamiltonian,
yes.
So then there should not be harmonization, it should stay in this eigenstate.
Exactly, but in this case, essentially, it already behaves like a thermalized state. I mean, essentially, the state. I mean, if it satisfies ETH, if you start with an energy eigenstates of the Hamiltonian, of course, you're right. There's no time evolution, so that Hamiltonian is time independent, so you will just get a linear curve. But if you now take a thermal state at a matching temperature and take the expectation value for this thermal state, you will see that this O thermal will be also very close to the expectation value in the energy eigenstate. And the reason, of course, is that at this temperature, the distribution in your ensemble of energy eigenstates in the thermal state will be peaked around the energy eigenstate that you selected before. So it is compatible, but you're right, that is kind of an extreme case where you won't see this process happening. Yeah. Okay, then let's continue. Very broadly, dynamics of Hamiltonians can be put into quantum chaotic models. Here, kind of as a cartoon picture, the corresponding classical version of a billiard, which generally satisfy ETH. So this phenomena just described occurs. And that means the exact dynamics and computing eigenvectors is quite complicated. But because of ETH, the eigenstate thermalization hypothesis criterion being satisfied, means long-time observables are generally easy to compute because you can use this trick to just do the thermal prediction. And then there are integrable models. And in that case, the dynamics and eigenvectors are less complicated. There exist analytical techniques to get them and understand it. But if you then actually want to compute the dynamics of observables, you need to use these analytical techniques. And it's not just predicting a single value. You will have a phenomena occurring. Yes?
So there's a distinction between many-body chaos in quantum physics and single-body chaos.
Yeah, so this is many-body chaos here.
Does ETH care between many-body and single-body?
It does to a certain extent. No? So in general, yes. I mean, if you have, for example, so we will actually have an example at the end, 3D Anderson model, which would be a case which is which you could call one-body chaotic, a random, but integrable from a many-body perspective. And we will see that they behave different and not ETH from the, from a general perspective, yeah. Okay, so this is kind of the broad scope. And now let's look at a concrete Hilbert space and a concrete system that, or class of systems that we can look at. And that is, let's start with fermions because there we have lots of techniques. Spinless fermions, in principle, they can also have spin in 1, 2, 3 dimension, doesn't matter. It can be in any dimension. We have some lattice, and we can say at each point we can have a fermion sitting or not sitting. So our state just describes where the fermions are. And we can define for a general pure state a bipartition into subsystems in any of these dimensions. The number of sites are a measure of the volume, essentially, in the subsystem and its complement. We can compute the Hilbert space dimensions. And we can also introduce a particle number operator that measures how many particles a state has if it's an eigenstate of the particle number operator. And we also can count the number of particles in the subsystems if the state has a fixed particle number in the subsystems. So we can compute all these quantities. And we can now introduce two real numbers between 0 and 1 that we will use to characterize classes of states, namely, or characterize the entanglement entropy. Namely, we can define the subsystem fraction, which is VA divided by V, which is essentially the x-axis in these plots that I showed you. Now, what size, or what fraction of the total system do I look at when I compute the entanglement entropy? And the second quantity is something new. That is now the filling fraction for states with a fixed particle number, where I divide the total number of particles by the number of sites, which due to Pauli exclusion will be a number between 0 and 1. Yeah? And with that, we generally know that the entanglement entropy satisfies the following three conditions. First, as mentioned before, it is symmetric under exchanging subsystem with its complement, which means if we plot the entanglement entropy with respect to F, it will have a mirror symmetry. That's the mirror symmetry that we already saw before. However, the entanglement entropy also satisfies a symmetry with respect to the particle hole symmetry, which means that if we exchange n, little n, with 1 minus n, it should also be symmetric, which means if we plot with respect to states with fixed particle number, we also expect a mirror symmetry with respect to this axis. And finally, as mentioned before, due to the finiteness of the Hilbert space dimension, there is an upper bound to the entanglement entropy, and together with the symmetry, that will define us such a triangle, or in this 3D plot, a roof under which any entanglement entropy will be. Okay, with these properties, let's now look at ensembles for which we can compute the entanglement entropy. And here, based on the question before, we definitely want to define ensembles that are nice enough that we think that they describe useful physics, but they are also nice enough that we are able to make analytical progress. Yeah? So not doing just numerics. And the first one is the case that I already looked at. It's just full Hilbert space, all pure states, which was already done by Don Page. But it should be part of these ensembles. Then another class of states that plays an important role in the context of free and integrable quantum systems are so-called fermionic Gaussian states. It's a subfamily, a submanifold in Hilbert space, and they are generally appearing as eigenstates of quadratic fermionic Hamiltonians. And then we discussed particle numbers, so we can now also restrict to states in Hilbert space with a fixed particle number. And of course, we can intersect the two and restrict to fermionic Gaussian states with a fixed particle number. And define that, that already gives us 4 ensembles of states. And in the context of eigenstates, if you don't want to restrict to fixed particle number, you can also take a statistical ensemble essentially of these different sectors with something like a chemical potential. And it turns out that this actually still plays an important role when relating things to all energy eigenstates, if you don't restrict to a subsector with fixed particle number. And then you can do the same thing also for Gaussian states with fixed particle number and then take a statistical ensemble over them. So those are the 6 ensembles. In this talk, I will mostly focus on the first 4. Okay? So what do we want to do with these ensembles? All of these ensembles define essentially subfamilies of our total sphere of pure states. And if we compute the average entanglement entropy for these families of states and take the limit of a large system, we generally expect that the average satisfies a volume law at leading order with some coefficient in front and then some sub-leading corrections. And let me just tell you how much progress there has been in terms of either finding a fully closed analytical formula or at least getting the asymptotic versus just understanding the leading order or special cases. So essentially until 2020, the only case that was fully understood was the case of pure states in all of Hilbert space. So that was from 93 by Don Page with a closed analytical formula and so on. Well, in all other cases, there have been studies, but they focus only on leading order or special cases. And what we accomplished was by combining expertise with Mike Keyborg and Peter Forrester from Uni Melb math department, who were working in random matrix theory, that provided crucial tools to make progress. And we could solve essentially 1b and 2b, so the Gaussian cases, completely analytical, computing the average and also leading order of the variance. And in all other cases, we could develop a systematic scheme to get this asymptotic expansion order by order, and in particular, we could compute it up to constant order. All higher orders will vanish for large V. Okay, so that's the first progress that I'm showing here in terms of our work. And let me just tell you these 2 cases, so 1 and 2. So this is the work by Don Page from 93 and kind of our analogous version now for the family of fermionic Gaussian states. These are the analytical formulas. They are all written in terms of the d gamma function. That's what Don Page found, and that's what we got. And now let's look at how we approach this for large V, what it looks like. So for small v, we already see that for small subsystems they are similar, but for large subsystems there is a difference. And as we increase, we clearly see that we reproduce a similar behavior as what I showed at the beginning, where we studied eigenstates. But this calculation is not done for eigenstates. It's not related to a physical Hamiltonian. It's just a calculation for the family of fermionic Gaussian states. And you can do an asymptotic expansion, and you see that this leading order is described by this analytical curve in terms of f, which is analytical up to half of the system. There is, it's not analytical at half, even though it looks very smooth. Here it's obvious that it's not analytical. And you also saw kind of the dimp that is just at half of the system, and that indeed is something that if you do an asymptotic analysis, gives you a Kronecker delta just at half of the system, which is something that was understood by Don Page and others in the 90s. Yes?
So are these for chaotic eigenstates?
No, this is not for eigenstates. This is just for the family of fermionic Gaussian states. It's just a set of states. It's a manifold of states where we can use random matrix theory to compute this analytical expression and find this average.
So you're picking random states, or you're picking
random fermionic Gaussian states with respect to the Haar measure. So it's essentially choosing random states in a sub-manifold of that sphere from before, namely the sub-manifold of fermionic Gaussian states. Yeah. Let's look at the same setting, but now with particle number conservation. So this is kind of in this review paper or tutorial style paper. For the general case, where there hasn't been so much progress and we still don't have a closed analytical formula, we are not sure if that can be even found, but we have a systematic way to extract the asymptotic expansion from such a complicated sum, while for the fermionic Gaussian states with fixed particle number, we have again a fully closed formula in terms of the d gamma function again, that now depends on V, the subsystem size VA, and also the particle number conservation, no? Which here, the total particle number in this family of states. And we can look what it looks like, how it behaves. And as we take the thermodynamic limit, we can do an asymptotic expansion. And what you notice is that for completely random states without further requirements except fixed particle number, we have lots of triangles. If you fix the n, they will all be triangles. While here we get again these round shapes. And again, if you compare it, like take the view, zoom in from here, you can compare and see that for small subsystems, the two are indistinguishable. It's really at large subsystems, at half of the subsystem, half of the total system, where we can distinguish between fermionic Gaussian states and random states, both with fixed particle number. And here, that is the analytical formula that is the asymptotic expansion. And here's the equivalent asymptotic expansion for fermionic Gaussian states. And you can show that the two match if you take the limit of f towards 0, and you just want to get the slope of the near small subsystems. Okay, so now I just told you that we are able to use random matrix theory to compute some averages. Well, that's a nice analytical progress, but what does that tell us about physics? So this is now where numerics comes into play. So far, these calculations use analytical tools, but we can now look at a Hamiltonian as one example, and in fact, this is a kind of a parametrized family with various parameters of a physical Hamiltonian that falls into this class. You can convert this Hamiltonian also to a fermionic system, but from the Hilbert space perspective, it doesn't matter because hardcore bosons are essentially also just local two-level systems. So from the calculation of entanglement entropy, they're equivalent for these state classes. And you can now compute eigenstates of this Hamiltonian analytically and then evaluate the entanglement entropy. And that's what was done here for eigenstates in green, for eigenstates with half filling, but also for filling at 1/6. And we compared these entanglement entropies to the ones of random states computed in the cases here before with these formulas. And what we see, and one can do a scaling analysis to verify that at leading order, they match exactly, depending also on n. Yeah? So if you focus on n1/6, you get again matching if you take our analytical formula for random states at n equal to 1/6. Okay? And we now tested various other quantum chaotic interacting models. Essentially, you always find this matching. But what if you look at a Hamiltonian that is not interacting, that we don't expect to be integrable? And here, the example that I mentioned is the three-dimensional Anderson model. It's a quadratic fermionic Hamiltonian with here a random particle number potential. So from a one-body perspective, this would be chaotic. But from the perspective of a many-body Hamiltonian, this is of course not chaotic, even though it's random, it's a quadratic Hamiltonian, so it's integrable. And what we did is we computed eigenstates of this Hamiltonian numerically and computed their entanglement entropy and compared that to random states, but now not random states in all of Hilbert space, but random states in the sector of fermionic Gaussian states. So the one where we have this lower entanglement entropy, the rounded curve. And again, we find excellent agreement in that case. So, and this work has now also been extended for other models. And the philosophy here is for quantum chaotic model, we expect that the left-hand side of this table is a good prediction. While for integrable models, you essentially can use the sub-extensivity, that this slope is not linear, but goes down for large subsystems as an indicator of integrability. And in fact, this has been now also extended in a study from 2019, where we were not, they looked at Hamiltonians that were not quadratic, but integrable interacting. Yeah? So it's not just something saying, okay, of course, if you just look at free models, essentially, they may be very well described by fermionic Gaussian states, but what happens with interacting models that are not quantum chaotic? And what we are claiming is they are still well approximated by the behavior that we see for pure Gaussian states. We're not claiming they're exactly like that, but that this behavior of a lower entanglement entropy is exactly the, a signature or a probe of the departure from quantum chaos. Yeah? So we have A here, interacting quantum chaotic models, this very well described by general pure states satisfying the respective symmetries, for example, particle number conservation. And then we have quadratic and more generally integrable models, and they are very well described by subfamilies in the case of pure quadratic models by pure fermionic Gaussian states. Okay, so any questions at this point? Yes.
So for a quantum chaotic model, it's surmised that the spectrum will agree with random matrices.
Yes.
Like the Gaussian unitary ensemble.
That's right, but here
It's just about the spectrum, whereas this is about the eigenstates. So my question is it expected that the eigenstates of a random Hamiltonian will be hard distributed? And would that, if that is true, would that explain what you see in your numerics?
So, I mean, it depends on how you construct your random Hamiltonian. But it is true that for certain, Gaussian ensembles of Hermitian matrices, it's of course true that the eigenstates are hard distributed. In that case, it's kind of a triviality to say that, of course, if you then take the average over all eigenstates and also average over kind of realizations of these random Hamiltonians, that the behavior will be the same as the ensemble that I show here. But the statement here is different because we're not looking at an interacting quantum chaotic Hamiltonian that is itself a random matrix. We are looking at a specific model that has local interactions, things like that. And for that, we know, or we can expect that the eigenstates have some features of being H-random, but not fully. And because, I mean, you still have imprint of the specific realization of that Hamiltonian interaction and things like that.
But it's like the statistics of the spectrum are relatively close to the random matrix theory prediction.
Yeah, that's
right. Just like what you're seeing in terms.
That's right. But I want to emphasize one other thing, and that is, if you do this analysis and this Hamiltonian has symmetries, this random matrix analysis really requires that you have a very detailed understanding of what symmetries this Hamiltonian has, that you do the right random matrix kind of spectrum analysis, like if you're talking about level spacing, for example. Well, this analysis does not require any any detailed understandings in that way. No, you just, yeah.
But instead, you need to know how to half random sample given your symmetries. It's like an equivalent from it.
And well, the statement here is that very broad classes of states. So, for example, for the symmetry of particle number conservation, you then don't need to know much more details about the specifics of the Hamiltonian. But moreover, the philosophy here is, of course, also just seeing that we have this linear dependence on the subsystem size versus something that depends on the size, which means in practice you don't even need to exactly compute analytically the kind of reference ensemble, but just study the entanglement entropy as a function of the subsystem size. There was another question.
If you dimerize your lattice, you will get CCH model that has two phases, trivial phase that have only localized states, and the topological phase that also have two edge modes.
Yes.
Could you distinguish them based on these approaches, ideas?
So yeah, boundary phenomena are something that, at least from the perspective of the average, so from these ensembles, are completely washed away. So there definitely are imprints on boundary effects and phases, but they are not at a leading order in the entanglement entropy. So there was one study that we did for quantumizing model, where depending on the boundary effects, you could see something in the first subleading term to distinguish if the model is so essentially in that context, the question was if we are critical or not. I now switch gears a little bit and just want to show you a very general result that we just put on the archive a few weeks ago, and that is focusing essentially on this setup, but now going beyond fermions, going towards a completely arbitrary system with fixed particle number conservation. Yeah, so the setup is we have again our lattice, but nothing related to fermions. If we zoom into an individual site, the only structure that we have is what is the dimension of the local Hilbert space that carries 0 particles, which is like the vacuum, not placing a particle there. 1 particle, so how many ways are there to have 1 particle, 2 particles, and so on. Yeah? And this structure alone, any Hamiltonian or quantum system that you give me, or a large class of them studying condensed matter physics, I can give these integers. And I'll show you an example in a moment. And that's the only structure, this sequence of non-negative integers, that will allow us to still compute the average entanglement entropy analytically and understand what's going on. Yeah? So that's this sequence of AK. And usually we assume that the vacuum is unique, so typically A naught is one-dimensional. But we could even deal with degeneracies here if we wanted to. And the Hilbert space sector of fixed particle numbers, after we have done such a decomposition into subsystems, can be written as a direct sum over tensor products where we distribute our n particles partially into A versus B. So let's just give 3 examples. Spinless fermions, that's the case described in the previous part of the talk. There, A naught is 1. There's one way to place no particle, and there's one way to place a fermion at a site, and we cannot place more than 1 fermion, so all other integers are 0. Other example, spin 1/2 fermion. In that case, there's again one way to place 0, 2 ways, spin up and spin down, to place 2, and then again just one way to place 2 particles, because Pauli exclusion principle, they need to have opposite spin, and we cannot place more than 2 particles. Last example, photon, a massless spin 1 boson. There is one way to place no boson. There are 2 ways, the 2 polarizations, like it's a 2-dimensional space, to place 1 boson. And if we wanted to place two bosons, for example, they could both be plus polarized, they could both be minus polarized, or 1 plus 1 minus, so there would be 3. And in general, you would find that for k particles, there are k plus 1 ways corresponding to the different ways to distribute the polarizations. So with that setup, how can we compute the entanglement entropy for a random state in this Hilbert space, in this space of fixed particle numbers? And more generally, one can relate this structure to a U1 symmetry that the particle number operator generates. Well, in our work from 22 and already before in 19, we essentially have a technique that relates this average to just a sum expression that only depends on the dimensions of the Hilbert space A, B, and the Hilbert space with fixed particle number in total. So psi is again the d gamma function that essentially behaves like a logarithm. And then we just need to understand these 3 dimensions. But these 3 dimensions are essentially just one function, because the subsystem B with a fixed particle number in the subsystem is of course just the same as the full system, just scaled smaller. So if we understand this function, we also understand the other 2 cases. So that's great. We can all compute it from one quantity. So if we are able to find that quantity, we should be able to plug it into this formula and see if we can do an asymptotic analysis. And how do we find the dimension of the Hilbert space with n particles in the setting that I described? Well, it's a combinatorial problem. We want to distribute n particles over v sites, and if we zoom into each site, we have different buckets. We have one bucket for the vacuum, but for example, for the way we can place one particle, we would have A1 buckets corresponding to the different ways to place one particle and into one side. And similar for 2 particles and so on. So that's the question. And we can use a standard combinatorial trick of a combinatorial generating function. We take a polynomial in these integers ak with an auxiliary variable z, take it to the vth power, and the claim is the dimension is just a coefficient in front of z to the n. And just to convince you, let's look at an example that works for a spin 1/2 system with 1, 2, 1 and lots of zeros, 3 sides, 2 particles. Let's just count. So placing 2 particles onto the first side, the second side, or third side. Well, placing 2 particles, there's always just one bucket, so there we multiply with 1. And because the vacuum is unique, there's also just always one way to place no particle. So those are 3 configurations that are linearly independent directions in Hilbert space that span the space of 2-dimensional, 2 particles. Now, placing 1 particle on side 1, 2, or 1, 3, or 2, 3. For each particle, we can choose spin up or spin down. So there are 2 possibilities. And so in total, we find 4, 4, and 4 with a total of 15. And that's exactly what you would get if you take this to the 3rd power and take the coefficient in front of z to the 2, which is z to the n. And of course, the reason is that this counting is just reproduced if you multiply out this polynomial. Yeah? So if you have experience in combinatorics, that's of course a triviality. But knowing that we want to get this coefficient in front of z to the n out of this polynomial to the power v, we can use complex analysis to isolate the coefficient in front of z to the n, because we know if we do a contour integral around z to the l, only if l is exactly -1, we will get 1 instead of 0. So that means we can now extract dn by doing such a contour integral of our polynomial, and we divide it by z to the n times z, which puts exactly the z to the n power to become z to the minus 1. Okay? With that, we can now massage the integral and introduce a function psi n, and we can take the limit for large V and do a saddle point analysis. And that allows us to extract the asymptotic behavior of the dn that we are looking for large V that is fully described in terms of a function called beta of n, that is the saddle of the function psi n, that is here defined just in terms of our integers ak and the filling fraction n. We need to evaluate this at a saddle where this function vanishes, and that gives us a function that purely depends on the integers and our filling, and that's all we need. And here I plot this function beta of n for the 3 cases. So with that, we have all the ingredients needed, because we can put this asymptotic expansion into our formula for dA, dB, and dn, and expand for large V. And I show you here for different sizes of the system. If we increase the system, this part becomes a Gaussian, this part becomes a function phi of n, and we can extract the sum in its asymptotics and get an analytical expression. And that's what we found, and that now applies to any system with a fixed particle number and is fully characterized just by knowing this integer sequence ak that is realized in here by knowing this function beta of n. So in summary, bucket combinatorics, saddle point, Gaussian integration, we arrive at this formula. Beta of n often can be found analytically, but you can also get it numerically in certain settings. That encodes everything we need to know. Oh, I'm sorry. I don't know what's going on. Okay, sorry. We always find a volume law at leading order. So we always get f times v, which is this linear slope that we also saw in the fermionic case. And interestingly, there's the square root correction, and the constant term does not depend on beta and is universal. We have some ideas where that comes from. And there's a Kronecker delta that also tells us something about the subleading behavior of the quantum correlations. That was the second part, and with that, let me just wrap up. First part, we have kind of this understanding of both the average, partially exact, and in its asymptotics of the average entanglement entropy and its variance. And in the case of a setup of Hamiltonian with fixed particle number conservation, we know not just the leading order, but also up to constant order in a reasonably compact formula. And we're currently in the process of comparing that to different models. And with that, thank you so much for your time.
I was wondering if this, so you can calculate some this entanglement entropy when for specific Hamiltonian, and then this Hamiltonian, they have parameters. For example, you have this kind of Hubbard model.
Yes.
And then you have the tunneling parameter, or some interactions parameters.
Yes.
And so how does this parameter affect this entanglement entropy? Because in this formula you have, it is dependent on the volume, so then are the parameters present in the constant in front?
So let me emphasize, the formula, the analytical formula is not computed for the eigenstates of a Hamiltonian, but for an ensemble. So that means this calculation just doesn't depend on the parameters of the Hamiltonian. However, What I'm claiming is that this analytical formula for this computed for this ensemble reproduces the same leading order behavior as if you did the calculation for your eigenstates. And in that case, these averages will depend on these parameters. But the claim is not at leading order. So at leading order, you will not get such a dependence. And at subleading order, we do expect this dependence. And then there is another subtlety. What happens if in your parameter space of Hamiltonians, you have lots of quantum chaotic models, but you have like specific critical parameter choices where your model transitions from a quantum chaotic model to an integrable model. And in that case, it's indeed true, and we have studied that numerically, that you have a switch where essentially from an initial, I mean, if you look at the eigenstates, the leading order reproduces this triangle, like our calculation, and then you go over to the integrable case, and you get a this rounded curve. But of course, in order to really see the switch happening, you need to do a finite size scaling analysis and take the limit for large V, and then you need to do a double scaling limit to understand like how close are you to the critical point, and do you still see the volume law or the sub-volume law. But you can do this analysis and you can see that it's exactly at the critical point where you have the swap. And if you're near, you need to kind of analyze which limit you take first, like approaching or volume to infinity.